Julie, welcome to the Astro Ben podcast. Thank you so much for coming on. How are you doing?
I'm doing well, thank you, and thank you for having me.
Thank you. I've been hugely excited to chat to you. Um, 'Cause you've been at NASA for a while now. What's it like working for such an iconic institution?
Oh, it's fantastic. I It really suits me that we're surrounded by really outstanding engineers. So if you have half an idea of something that you'd like to do, you're surrounded by people who can help make an idea for a mission or something turn into reality. We're also really big at Goddard Space Flight Center. We're have a very strong astrophysics division. And that also means that if you're interested in studying some scientific area, it's easy to find other people who have expertise in all the things that need to come together if you want to make a major result. So, for example, if I'm studying a an active galaxy and I want to add X-ray observations, there's an X-ray person to ask information from.
So it's a whole ecosystem of the best in the business. Um,
Exactly.
that's fantastic. I've only bizarrely on this podcast, I've only had one other person on who works for NASA, despite having done nearly 60 episodes. A few weeks ago, actually, Aurora, who a sort of similar line to yourself, she works in searching for exoplanets.
Ah,
Um,
okay.
but I'd love to come on to your area of focus at the moment. But just to go back a little bit, I was just kind of wondering where your fascination with the cosmos and physics started from. Was there a sort of moment where you looked up at the stars and got inspired by the cosmos, or how did you get into the industry?
So there has never been a moment where I wasn't really interested in learning how the world worked. I mean, my whole life I loved scientific topics. So I really, cared about, how do rainbows happen? Why is the sky blue? And then as I, was getting a bit older and, doing sort of O levels and A levels, and I realized that what I was interested in was sort of the fundamentals of how the universe is, uh, what the universe is. Which led me to being interested in either particle physics or astrophysics, and I've ended up taking the astrophysics path. And so I can't imagine, there hasn't been a eureka moment because I'm doing following my interests has been something I've been able to do my entire career, and there's never been a moment where this isn't what I've wanted to do.
Wow, that's so inspiring to hear. I'm sure a lot of people listening to this, they all want to find their kind of follow their passions and NASA has sort of afforded you to end up where you are, which is great. So let's talk about the Nancy Grace Roman Space Telescope, because until I read your bio, I had never heard of it, and that's for obvious reasons. It's a telescope that is in the pipeline, and so it hasn't sort of been talked about too much. With obviously the focus at the moment being on the quite rightly so on the James Webb Space Telescope. So let's start from the beginning. Sorry. So the Nancy Grace Roman Telescope. What is it, and how did you get involved?
So the Nancy Grace Roman Space Telescope is a telescope that has the same size uh, mirror as the Hubble Space Telescope. But it has a much larger field of view, which means it sees a much larger swath of the sky in any instance. And it's designed to very efficiently tile large areas of the sky to conduct surveys. So what that means is that, for one of our major surveys, it's to look at 2,000 square degrees of the sky, and we'll do that survey in about a year. That same observation with Hubble would take over 1,000 years. And by being able to make those kinds of observations, we're doing science differently. So with the James Webb Space Telescope, what you are, I think the analogy that they use is a, sort of a grain of, grain of sand held at arm's length. So you're seeing a very small patch of sky with exquisite detail and sensitivity out to the beginning of the universe. So when you have an observatory like that, what you do is you point at a object that you already know about. Conversely, with Roman, because we're tiling the entire sky, we're not looking at a particular galaxy. What we're doing is mapping out a large region of the sky to find billions of galaxies. And with those billions of galaxies, we'll measure precisely the position of and shape of hundreds of millions of those galaxies. And we'll precisely measure the distance of tens of millions of those galaxies. And from that, we can build up a picture of how the distribution of galaxies has evolved from the Big Bang through to the present time. And that will tell us all about galaxies. It will tell us about how structure has formed. It'll tell us how the universe has expanded, and by extension, where the universe is going.
Wow, that's totally mind-blowing. And I guess it's it's quite fitting that you're the project scientist. For those that don't know, Nancy Grace Roman was a very well-known American astronomer, and she was the first female executive at NASA. So that's quite significant. How do you feel about that? Do you feel an added sense of pride that you're on that project?
Yeah, I actually do. It's really nice when the observatory that you work on is named after somebody you personally admire. So I knew Nancy Grace Roman, and she was really quite a spectacular lady. She was very, very sharp, and she understood both the science, but also the engineering and the management and the politics. So, like all the things that you need to bring together to make a NASA mission go.
And she also had the known to many as the mother of Hubble. I've been reading.
Yes. Yes.
Which it's sort of come full circle. I think that's brilliant.
Yeah, although sometimes I think calling her the mother of Hubble, downplays what she did, because I think you could also say that she's the mother of all space-based astrophysics, because she started that program and was behind a very large number of missions, not just Hubble.
Fair enough. And the big question for impatient space fanatics like me is, when will the launch be? Now, obviously, we're a few years away yet, but when's your, to your best knowledge, when do we hope to see the Nancy Grace Roman Space Telescope in space?
Well, we have, made a commitment that we will launch no later than May 2027. But as you can tell from the way I'm phrasing that, that's a no later than date. Internally, we're actually working towards an October 2026 date, and we're really hoping that we can actually launch a little bit earlier than the date we had promised.
Oh, that's cool, and it sounds really far away, but we're basically in 2023 already, so it's actually not.
Oh, it's terrifying! It's not far away at all.
No.
What's it? Also, I mean, being as close as we are means that it's a really fun phase of the mission. We've put together our flight camera. The 18 detectors are in the camera. Every test that we make is now a test of how the kit that we're going to put in space is actually going to perform for science observations. So each week we're learning something new, and it's beyond exciting to see it all come together.
I bet. So is it currently being constructed in a clean room? Is your day-to-day going in and seeing it being built, or what's day in the life?
Well, so there are parts of Roman being built in many different places. So, for example, last week I was in Rochester, where L3 Harris, who are responsible for building our telescope, to have a meeting there and to look at the hardware. And right now, if you look at it, the part of the hardware that has the secondary mirror and the struts going down to the assembly, going down to the sort of the holding ring, is all put together. So it looks very much like a telescope. The primary mirror assembly is, also complete and ready to go. Obviously I don't work in Rochester day to day, but there's a group. That's what one group of people are doing. Later in December, I'll be visiting Ball Aerospace, who are responsible for putting together the um, mechanical assembly for our primary science instrument, the wide field instrument. And that's also really cool. Like, they've put the filter wheel in, they've shown that it moves and operates correctly. At Goddard, we're building the focal plane, so the detectors, the electronics that sort of take the light that comes in and converts it to electronic signals that you then use to make the pictures of the sky that will do the Roman science.
That's so cool. How does it feel seeing the success in multiple ways of the James Webb Space Telescope? Does it sort of make you feel more excited? Does it put the pressure on a little bit, knowing how much impact it can have when these missions go well and millions and probably billions of people around the world see the images and hear about it almost instantly on their phones? Or do you not really think about that?
Oh, I definitely think about it. I love to see the new science results that are coming from the James Webb Space Telescope. I mean, I think it's completely inspiring. I think it's incredible that we spend a very long amount of time putting together a mission like JWST. And when it launches and when we start, after we start taking the first images, you can really see, yes, this really was worth it. And it took a long time because we're doing hard things. Roman hopefully won't take quite as long to come to pass, but I'm very much hoping that our results are just as groundbreaking, just in a different way. So instead of seeing deep, we see wide.
Interesting. So I'm going to ask a very stupid question, just going back onto what you said as to the coverage of Roman. So you said 2,000 degree coverage. Do you mean, like, is that the total amount of space from a point on Earth? Well, it's not on Earth, obviously, but from the point of the telescope, is that sort of where that comes from? Is the sort of full coverage?
So I didn't describe that well. So our actual field of view is not 2,000 square degrees. So our field of view is kind of zero point 0.4 by zero point 0.8. I can't remember what that is in terms of um, size of the full moon, but it's larger than a full moon, but it's not a large swath of the sky. To get to the 2,000 square degrees, what we're actually doing is tiling.
Oh, I see. So you take it, so you sort of build up a picture.
Exactly.
Mm.
But the reason that I mentioned the survey is that if you think about what it takes to survey a region of the sky, having a large field of view is just the first part of it. We're also designed to slew rapidly, stop on a dime, be ready to take the next observation. So we're designed not just to have a large field of view, but also to be able to do this kind of survey very efficiently.
Mm. That's so cool. So thinking about the aims of Roman and what you hope to achieve, I've sort of done a bit of research, so I have a bit of an idea. But it'd be great to kind of hear it from yourself. So, getting answers to questions about dark energy, from an astrophysics point of view, I'm sure is hugely exciting. So, how is the telescope going to tell us about the history of the universe and answer questions about dark energy?
Well, that is a great question. Our uh, our strength with Roman is that we can measure dark energy in multiple different ways. So I mentioned before that we have this 2,000 square degree survey of the universe, and in that region, we will be measuring precisely the positions and distances of tens of millions of galaxies. Um, And that allows us to explore how structure formation as a history of time. Those same observations will also allow us to explore the expansion of the universe as a function of time. We will have a second survey that will take a few tens of square degrees and go back every 5 days. And that kind of data set allows us to detect supernova, and those supernova will provide us with the data that we need to measure the expansion history of the universe as a function of time. But I think I'd like to go back a couple of steps and explain what we mean by dark energy and dark matter. So if we look at a pie chart of what the universe is made of, normal matter, the kinds of things that makes up stars, planets, us, is only 5% of the energy in the universe. Around 28% is what we call dark matter, and this dark matter is we know it's there because of its effect, gravitational effect on other material. But otherwise, it behaves quite differently from the normal matter that we know of. So dark matter was discovered when we notice that the motion of stars around a galaxy is much faster than you would expect based on the material in the galaxy itself. And then we understand the waffling a little bit here, but the third component is dark energy. And dark energy is a repulsive force, and it's a surprise. So if you cast your mind back to the 1990s, when people were doing experiments to measure how is the universe expanding as a function of time, and if all you know about is that there's been a Big Bang that sets everything expanding out into the universe, and you think that the only force that you know of is gravity and normal matter and dark matter, you would expect that the presence of the matter and ordinary matter is going to slow things down, right? Gravity tends to want to pull things together. And what they actually found is that the universe is accelerating, which means that there's something really fundamental about our universe that we don't understand, something really fundamental that is causing a repulsive force is causing things to accelerate. So one of the primary goals of the various Roman observations is to look at the growth of structure as a function of time, which is very strongly affected by the nature and distribution of dark matter, and to look at the expansion history of the universe as a function of time, which is very strongly affected by the nature of dark energy, and dark matter. And from that, try and tell us a little bit more about how our universe works.
Wow, thank you so much for breaking that down for me. You could probably tell by the look on my face I needed a bit more explanation. But that's great. And what's I guess your job as the sort of scientist on the project is you're asking the questions, but do you also have a sort of hunch or a prediction on what we might find, or do you try and not let that bias any of the science? What's your sort of answer to that, if you don't mind?
Well, so I mean, sorry, I'm distracted because my puppy is at my feet chewing something he shouldn't. But okay, I've got it under my foot. So I'm always optimistic. So I'm confident that we will, make exquisite measures of dark matter and dark energy in the way that we had planned. But the observations that we make to get there are discovery in nature. Right? What we're going to survey a huge region of the sky with unprecedented sensitivity, with unprecedented sharpness. We're going to survey large regions of the sky in time, again with extraordinary capabilities. So I think that the most exciting results to come from Roman are going to be something that we know nothing of yet. What I'm hoping is that we make really unexpected new discoveries. In previous when you look at the universe in a new way, you find new things. So sorry, still puppy. If you look at the universe in a new way, you find new things. So, like previous missions have found gamma ray bursts heralding the birth of black holes. We can find evidence for stars being the emission produced when stars are swept into supermassive black holes at the center of galaxies. So what I'm really looking forward to most with Roman is the surprises, is the things that that we don't yet know about that will create the new questions for the next generation of astrophysicists to address.
So exciting. And I guess another sort of area that certainly excites myself and a lot of the general public is when we start talking about exoplanets, and part of Roman's focus is to help answer new questions about the potential for life in the universe. I'm not going to ask you to predict that because I think it's the same sort of thing. It's like we don't know, but how is Roman going to be optimized for looking at exoplanets? Is it kind of an ongoing thing, or are you going to be searching specific stars to try and narrow down, sort of Earth 2.0, that kind of thing?
Well, I'm really glad you brought that up because that's kind of the other whole area of Roman science. So we will study exoplanets in two very, very different ways. One way that we're going to do this is to take our large field of view instrument, survey 2 square degrees towards the galactic bulge. So that's towards the center of our galaxy where we will see the largest number of stars. And we repeat those observations every 15 minutes. And in that data set, we will have hundreds of millions of stars. And each one of those hundreds of millions of stars will have a measure of its brightness every 15 minutes. And that allows us to detect planets via a technique known as microlensing. So as we travel around the galaxy, every now and again, there is going to be a chance alignment between a star in the galactic bulge and a star that's closer to us, where the star that's closer passes in front of the one behind. And when that happens, an effect called microlensing, where the light from the background star is lensed by the gravitational potential of the nearby star. And what we see in our data is an increase in brightness. And we see an increase, and then as we continue to move around and the star moves away from that alignment, it dies down again. If that star in the front has an exoplanet, what we see is an increase, starts to decrease, and then another increase as the exoplanet itself causes a little microlensing. And the reason this technique is so important, is that this technique is sensitive to planets at sort of the equivalent of 1 AU, so the Earth's distance from the host star out to the outer solar system and beyond. And most of the planets that we've found to date are the equivalent of in the inner solar system. So what Roman will do is complete our picture of a census of stars. So when you combine Roman with the stars with the exoplanets that have been found by Kepler and TESS, who see things close in, we will then have a complete sample from the inner solar system all the way to the outer solar system, and we'll have a much better sense of the distribution of planets around other stars. But that's not the only thing that we do. We also have a second instrument, a coronagraph. And the coronagraph is an instrument that is designed to suppress light from a star so that you can directly image a planet next to it. And this is very challenging. So if you wanted, for example, to image a Earth-like planet around a sun-like star, it's the equivalent of being able to measure one bioluminescent algae next to a lighthouse from thousands of miles away. So this is a really, really hard problem. And the way that we address this is, I sort of think of it as using physics as magic. So we view we make an observation of a star through a mask. And as the light from that star passes through the mask, it creates a diffraction pattern that gives destructive interference at the position of the star. And destructive interference effectively means you've switched the light off, which then allows you to image any planets that are around that star. So with Roman's coronagraph, what we will be doing is a technology demonstration to show the use of deformable mirrors in space. This is such a hard problem that you need to measure the properties of the light as you're looking at the star and automatically adjust the shape of your mirrors to compensate for small changes in the wavefront of your optics, because the diffraction pattern has to be spot on. And so if we're successful, we will be laying the building blocks for the NASA, sort of major flagship astrophysics mission to follow us, which will be building a coronagraph on a much, much larger scale.
Wow. And that will mean sort of direct images of planets potentially similar to our own.
Absolutely. Direct images of planets similar to our own, and I think even more crucially, directly measuring the spectrum of planets that might be similar to our own, so that we can look for sort of signatures of the chemistry that's happening in those planets. In other words, is it something that could host life?
Wow, what an exciting time to be alive. I'm very grateful for you to come on. This is it's so interesting to me, and I can't wait to follow your journey and Roman's journey. Is there anything else that you can mention about the mission? I know NASA announced that Roman would be launched on a Falcon Heavy, which everyone loves seeing a Falcon Heavy, which will be ready by October 2026. But is there anything else you can say about the mission that's sort of hot off the press, or?
Normally, I'm prepared for this. Not really, because you've touched on most of the things that I would come back to. I mean, I guess my main thing is that because we're all the pieces of the hardware that we're going to fly are, coming together right now. Things are going to develop really quickly. We're, in parallel with the telescope coming together and the instruments coming together and the spacecraft coming together. We're also really ramping up how we're working with the scientific community to decide how are we going to use this observatory. So there should be lots of conversations, across the entire astrophysical community on exactly what kinds of surveys are we going to do with Roman, which is of course tied to exactly what kind of science we want to do. In our discussion today, we focused on what can we do with cosmology, understanding the history and fate of the universe, and exoplanets, planets around stars other than our own. But we're going to do so much more. We're going to study galaxy clusters. We're going to study the properties of individual stars. We're going to map the distribution of dark matter in our galaxy and galaxies nearby to us. So the conversations that I think we're going to have over the next couple of years are, how do we make sure that we do observations with Roman that can address the largest range of science? And I think that that's going to make the next couple of years a really exciting time, because we want as many scientists as possible to let their imaginations run wild and help us uh, plan the best surveys we possibly can.
It's inspiring to listen to you, and I'm sure a lot of my listeners would agree. What advice would you give to young aspiring astrophysicists or scientists who listen to you and hearing you working on a mission named after Nancy Roman? What advice specifically for young girls and people from underrepresented backgrounds? The industry is changing, and you've sort of been on you've been on the NASA side for a while. What should people be doing, and what sort of advice would you give, really? Because as I said, it's inspiring to hear your story.
Well, I couldn't say that I'm, uh, that I know better than anyone else on the way to do things. I can say what has worked for me. I've always taken where I've had a career decision to make, I've taken the one that seemed to be most fun, not the one that was necessarily going to be like a long-term secure job or the highest pay or the highest status. So I would say, to people, if you're interested in something, pursue it. And also be aware that you can change your mind. It's fine to do something, and if it's you go down that path and it's not quite what you want to do, there's always an opportunity to redirect. I think occasionally we convey the impression that it's kind of a continuous track, from school to university to a PhD into a job, and that once you've gone down some path, you're locked into it. And you're just not. There's lots of opportunity to you know switch and do something else and come back. So don't panic.
That's fantastic, Julie. Thank you very much.
Thank you.